Welcome back. Today we're revisiting the idea of sequences that we had last week, and this time we're going to kind of look at the textbook. We'll see some of the same things that we saw last time around, but we'll kind of build on those ideas a little bit. So just so we remember, what do we mean when we say a sequence converges? Well, a sequence converges. A(n) approaches some number L. And by the way, I'm going to kind of stop drawing these curly brackets because I'm getting a little lazy, and I noticed the book is getting a little lazy. They're kind of not drawing them always either. So we'll just say A(n) approaches L if, and remember this is our definition, if for all epsilon greater than 0, there exists a capital N such that if n is bigger than capital N, then we have this inequality A(n) minus L is less than epsilon. And let's just revisit for a second what we mean by that. And what we mean by that is that we have some sequence here, and we have some L right here, which I'll just draw as a vertical line. And the sequence converges. What does it mean for the sequence to converge? Well, remember we could draw our picture with these dots. Maybe our sequence looks something like this, like that. But all this means is that you start with the epsilon value. So you start by taking epsilon value. What is the epsilon value? The epsilon value is a distance really close to L. So think of epsilon as that distance right there, really close to L. And then we draw a little window around L. And maybe the window looks something like that. So you start with epsilon. Once you've created your epsilon, you can then move over and find an n value. And so the n value depends upon epsilon. And that means we come over here and we find the n value. And the n value is the value where from then on our function is bounded by epsilon, or our function is within epsilon of L. So notice for this graph, n somewhere around here works because this part of the graph, notice every dot is within the range. And that's what this inequality right here is telling us. This inequality is telling us that each of those dots within the range. Okay, this is just a reminder. We've done this multiple times, so hopefully that was not news to you. But, I know that sometimes we have to hear these things multiple times before they really start to make sense. So with that being said, we'll keep revisiting these things over and over and over again. But today I'm going to introduce just a couple new ideas that showed up in the chapter. The first idea was one of subsequences, and this kind of makes sense if you think of sub things we've had in other classes. We have subsets, which is a set within a set. We had, if you took algebra, you had a subgroup, which is a group within a group. Or a sub-ring, a ring within. So we have lots of these things. We use the word sub, and it usually means something within something else, and that's exactly what we mean by a subsequence. So if our sequence looks something like this, where these values are x1, x2, x3, x4, x5, x6, then a subsequence, all we do with the subsequence is we just do some collection of them. So maybe we'll grab that one and that one, maybe we'll skip a couple, and maybe we'll skip a couple. And so maybe our subsequence looks something like this, x1, x2, and then the next one would be x5, x6, x8, x8, x9. So what you see is that we have some collection. So our subsequence is the same sequence values moving in the same sequence order. It's just we might skip some. So we've taken some subsequence of the sequences that we have. Okay, so once we've done this, there's a really nice way to characterize it. And so if we wanted to define this precisely, we'd say that a subsequence we might write like this: A(n) with a little k is a subsequence of is a subsequence of n when each n of k is a natural number such that n1 is less than n2 is less than ... Okay, so what's the big thing we need to do? The big thing we need to do here is we need to we need to just make sure that these indices, whatever you're doing here, we should need to make sure that these numbers grow larger and larger and larger. So let's do a quick example. Let's do a quick example, and a quick example might look something like this. We might have the sequence 1 over n, which we've seen a bunch. And what does the sequence 1 over n look like? It looks like, 1 over 1 is 1, and then 1/2, and then 1/3, 1/4, 1/5, 1/6, okay, etc. So these are the 1 over n's. And so we might take a subsequence. A subsequence might look something like this. We might have a sub n of k. Might be a subsequence where we take only, say, the odd values of these sequence. So there's multiple ways to write that. One possible way to write that would be a, say, n, 2n minus 1. So that might be one way to do it. And what you'll notice this will give us is this will give us the sequence, if you put 1 in, oh, hold on, wait, it went crazy on me. Okay, then if you put, then if you put 1 in, then we'd get a of 1. But then if you put 2 in, you'd get a of 3. Oh. All right. Well, sorry, folks. This is what it's like to not make these videos for a living, but to, I guess technically I am making them for a living. But this is not. I'm not hired for my video quality skills. I'm hired for my math. Okay, so we've got A1, A3, A5, etc. And if I look at that, that would be this first term here, the third term here, the fifth term here. What else would that mean? That would be the sequence. If I wanted to write the sequence out, my sequence would be 1, and then 1/3, and then 1/5, etc. Or if you're right, we could even write this as the sequence 1 over 2n minus 1, right? So these are all reasonable ways to think of this, but this sequence is a subsequence of the sequence 1 over n, because it's not every value of 1 over n, it's just some of them, and it's, in this case, we made it every second value of 1 over n. There'll be lots of ways to think about this and write this, but they're going to actually be really useful for us as we get to solving some of the more complicated theorems for this semester. One of the first things that we want to be able to prove is this statement, which is if x converges to A and x and k is a subsequence, then we want that subsequence to converge to A also. And by the way, that makes sense, right? Because that makes sense because if we look over here, if our sequence is converging to 0, our subsequence needs to be converging to 0 because it is also made of the same elements that converge to A. So how do we prove this? The proof isn't so bad. We do the proof kind of like you might expect, and that is we're going to let xn and A become less than some epsilon, and then notice that well, our subsequence has to be bigger than those k's. So first we'll notice n sub k is greater or equal to whatever that k is for each index n sub k, and that makes sense, right? So if we come back and look at this example, our third number in our subsequence, well, the furthest it could be is the third number, but if we skipped any, then it's actually the fifth number. So, you'll notice your subsequences are always further down along the line of your sequence than your sequences are. So whatever your subsequence term is, it's going to be greater than if we took the same term in the sequence itself. Okay, so once we make that observation, we just let epsilon be greater than 0, and we notice notice that there exists some capital N such that x of n minus a is less than epsilon for all n greater than capital N. But then, if k is greater than that capital N, n sub k, which is greater than or equal to k, is also greater than that capital N. So x nk minus a is also less than epsilon. And that basically ends our proof. So really the proof here was pretty simple. The basic premise was that this sequence right here, the x of n sequence, gets really close to a. This sequence is further along the line than x of n is, so that sequence also has to be really close to a. Okay. But what's nice about this is, let's come back and let's look at a consequence. This means every subsequence must converge. So let's really quickly notice that there's a converse to this. Converse, we might say this: if two subsequences of xn converge to different values, then xn does not converge. So notice, because our sequence says every subsequence could converge that same number. So if you get two subsequences going to different numbers, then that means that it doesn't converge. By the way, you could also say if you find any subsequence that doesn't converge, then that means that your sequence doesn't converge. So that's an alternate definition. So if any subsequence does not converge, then xn does not converge. Okay, so hopefully that makes sense. But what's nice is we can come back to this -1 to the n sequence, and now we have another way of proving this. Notice last time we proved this by using our epsilons and kind of taking epsilon maybe to equal to 1/2 or something, and showing that you eventually always have values that are close to 1 or equal to 1 and equal to -1. And so there's no way that you could get within 1/2 of your L, because there's no numbers that's within 1/2 of both 1 and -1. Okay, so that makes sense. But now we have a second proof. So this is a new proof to this problem. And my new proof to this problem looks like this. Notice, take the odd terms as a subsequence. And if we take all the odd terms for a subsequence, then we get the following. Then we get that the subsequence a 2n minus 1 ends up just being the sequence. Well, notice that's -1 to the 2n minus 1. But that, notice if you put 2n minus 1 in here, you end up just getting -1 over and over and over again. So we end up getting -1, -1, -1, -1, and this sequence converges to -1. But similarly, if we take the even terms as a subsequence, then if we take a to the 2n, well, that's the sequence -1 to the 2n. But this is positive because we've always, raised our sequence to an even power. So this is just the sequence 1, 1, 1, 1. But that sequence converges to +1. So since the two subsequences approach different numbers, different different limits implies no limit. Okay, this is not written very eloquently, but I think you all get the idea, right? And that is that because these two subsequences are approaching different values, this value and this value are different, then that means the original sequence can't converge to anything. So this one does not converge. And this gives us kind of a new way to prove things don't converge, which sometimes is actually a lot nicer and a lot easier than messing with all of our epsilon things. Okay, let's come to another theorem which kind of combines some of the things we talked about on Thursday and some of the things that we thought about with sequences. And that is, if E is a set that has a finite supremum, then there exists a sequence in E such that xn approaches the sup of E. So let's think about that. So first, let's kind of get a picture in our head of what's going on here. And that is, we have some set. What we know is we know that that set has a sup right here, which we'll call S. Now, and then that set is made up of a bunch of different points. So let's just put kind of circles on here. So that set is made up of a bunch of different points. It could of course be like an interval of points, but it could also just be a bunch of isolated points themselves, right? And it's possible that the point S is included, but it's also possible that the point S isn't included and that these get closer and closer to S. Well, all it's saying is that once we do this, what we can do is we can order these points so that we just choose maybe this to be our first point, and then maybe choose this to be our second point, choose this to be our third point, and all it's saying is that we can consistently choose points closer and closer to S, so that this sequence, x1, x2, x3, x4 converges to S itself. So we can just choose some way of collecting these points in E that converges to S. Now, I want to make one quick observation, and that is, notice this theorem doesn't say that every x1 has to be different. So if, for example, our set E, so if, for example, S is right here, and if say set E is just the numbers 0, 1, and S, so suppose those are the only 3 points on our term, then what sequence might you use? Well, you might just use a sequence that looks like this. x1 equals x2 equals, and we'll just let all of those equal S itself. So this sequence would just be the sequence S, 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 S. So if at some point you hit the supremum, then it would make sense that you could just create like a cheating sequence that's just whatever that supremum is over and over and over again. Because we didn't say that every point can only be used once, right? So we could potentially use those points over and over and over again in this theorem if we needed. So just to make that clear. But how do we go about proving this? Well, the way we're going to go about proving this theorem goes from using one of the things we did last time, and that is we have this theorem from last time, which said if you have a supremum S and you have a set E, then you take the supremum of E, which is that S, and subtract any little epsilon amount from it. And then you take the supremum of E itself. You can always find some value of E in between that supremum and any amount smaller than the supremum. Why is that? In my mind, that's because this supremum right here, this would be the supremum if there were no map values bigger than it, right? Okay, so this is the big idea. So all we're going to do is we're going to take this supremum and we're going to drop back some epsilon amount, and then we're going to drop back some smaller epsilon amount, and then we're going to drop back some smaller epsilon amount. And notice that we can always find points in every one of these ranges, and so therefore our sequence has to be getting closer and closer and closer. So I'm just going to sketch this proof, but the way the proof might look is something like this. We might say, create a sequence xn as follows. For each n, choose xn such that, hold on. Oh, I didn't mean to erase. Okay. Choose xn in E such that the sup of E minus, let's not use epsilon, let's do 1 over n, is less than xn is less than or equal to the sup of E. And then what you'll notice is that each xn is within 1 over n of E. And so, then this sequence, and this can be found by the, I think we called it the approximation principle. Maybe that's that. I remember I had the word approximation. I don't remember the exact name. Okay, by the approximation principle. Okay, so that means xn is within. So that means that for each n, and then for each n, the magnitude of xn minus that sup value is always less than 1 over n, because it's closer than 1 over n. So this obviously shows that this sequence xn is going to converge to that s, because take any epsilon and there's a 1 over n smaller than epsilon. Okay, so this is kind of the gist of that theorem and how we prove it. Okay, but this is actually going to be really useful because there's going to be a number of times that we are going to want to just create sequences, and finding a supremum then lets us create sequences that converge to things. Because we're going to have some proofs, especially some more complex proofs, where we want to say there is a sequence that does blank. And the first thing that you need to do is you need to know there's a sequence that converges, and then we use that convergent sequence to solve the rest of our problem. All right, so let me just say a few things before we get on here. There are some things in this section. So most of this section covers things we've already talked about. It did things like show that a specific sequence converges to a specific number, show that if two sequences converge and you add them together, it converges. There are a couple things that we skipped. So there are a couple skipped theorems. One skipped theorem is the theorem of what happens if you take two sequences and divide them by each other. Well, if you take two sequences and divide them by each other, it should approach the sequence A over B as long as that B is not 0. But you have to be a little bit careful when you do this thing, because we have to, this is similar to the multiplication task where we bounded it, but we have to be careful to bound B in such a way that B can never be 0 for any of the parts of our task, because once B becomes 0, then once B of n becomes 0, then that messes everything up. So this is a theorem that's kind of similar to some of the others. If you think this is something that might show up in a presentation or homework problem in the next day or two, then good job, you kind of know what I'm thinking. Another skipped theorem is the comparison theorem. And the comparison theorem simply says this. It says if an is less than bn for all n, then what they converge to must be less than also, right? And this makes a lot of sense. What are the assumptions here? You're assuming that both of these sequences converge. If they diverge, then all bets are off. Okay, so what I want you all to do for our task today. Again, these things will show up, like I said, in presentations or in homework. If you'd like to go ahead and work on them, that would be great. But for our task today, I really want to think about the question of what does it mean for a sequence to approach infinity? This is actually in the textbook, but I think I'd rather you try to think of it on your own. So let's go through this exercise for the first few minutes of class. What would it mean to say that x approaches infinity, and how would we define x approaches infinity? What would that? What are these examples, and what is that definition? And can we create the definition? It's actually really similar to what we've done so far. We just have to kind of change the roles of some of the things ever so slightly. All right. I have a second video coming up for class on Monday. That video is going to result in us proving one of the really big theorems for the semester, but it also has some more interesting things coming from sequences. In particular, it's talking about sequences that always increase or always decrease, and these end up being quite useful for us. So I'll see you in that video. So.